Hello. I'd like to talk about a very useful result to check the independence, actually conditional independence, for Gaussian random variables. So let's say I have three variables here, x, y, and z, and we will have x and y are conditional independent given z if we have rho xz is multiplied by rho yz is equal to rho xy, where this rho the correlation coefficient of the pair of each pair of variables, and the proof is rather straightforward. First thing, we just need to realize that, like, without loss of generality, we can just assume the variables to be zero mean and also like have unit variance. Otherwise, we can just subtract the means and scale it. So, and if we have variables zero mean and unit variance, then we can write the covariance matrix of the three variables as following. So basically, the covariance matrix is just if the diagonal term will be equal to 1 because it has unit variance for each of the variable, and the off diagonal will be just for the correlation coefficient, because for the off diagonal term, basically, for example, this will be expectation x minus x bar y minus y bar for the original, like okay, for this component here of the covariance matrix is supposed to be this one, but for rho xy it will be this over the variance also, expectation y minus y bar square something like that. But of course, because we already mentioned it's unit variance, so therefore the expectation of xy actually is the expectation of xy, because it's zero mean would be just equal to rho xy, something like that. Now, with the covariance matrix in place, we can just use this formula to find the conditional distribution of x and y given z. This is a very useful formula. I think I talk about this in another video. So it's basically it's something like if you have a random variable x, after some observation y, you have basically this is sigma xx is your original covariance. It will become smaller because of the observation, and smaller by sigma y inverse multiplied by sigma xy here and sigma yx here. And when, let's say, if everything is scalar, then basically sigma y inverse is just 1 over sigma y squared, is just the variance of y. So you can see that, like, when the observation is more precise, then you have the sigma y square inverse, or sigma y inverse will be bigger, and then like after the observation you have your variance will get smaller. So it kind of makes sense, the whole equation. So anyway, so we have the equation, we just substitute that in into the equation. Sigma cc here is just equal to 1, so it's and this sigma y xy c is just rho xy and rho xc and rho yc and so on. So then so then immediately we'll get the off diagonal term here. That's the thing that we are really interested in. Will be equal to 0 when this condition is given by this tiny lemma is satisfied. So because for Gaussian random variable, of course we started with Gaussian random variable, And for Gaussian random variable, after conditioning, it's still Gaussian random variable. And for Gaussian random variables, uncorrelated list is the same as independence. So therefore, like when this is 0, we have x and y uncorrelated, and this also implies that they are independent given the condition C, given the information C. So okay, that's all for me today.